Now that we've seen a few examples of historic ciphers, all of which are badly broken, we're going to switch gears and talk about ciphers that are much better designed. But before we do that, I want to first of all define more precisely what a cipher is. So first of all, a cipher is actually, remember, a cipher is made up of two algorithms. There's an encryption algorithm and a decryption algorithm. But in fact, a cipher is defined over a triple. So there's the set of all possible keys, which I'm going to denote by script k. This sometimes I'll call this the key space, the set of all possible keys. There's the set of all possible messages, and the set of all possible ciphertexts. Okay, so this triple, in some sense, defines the environment over which the cipher is defined. And then the cipher itself is a pair of efficient algorithms, E and D. E is the encryption algorithm, D is the decryption algorithm. Of course, E takes keys and messages and outputs ciphertexts. And the decryption algorithm takes keys and ciphertexts and outputs messages. And the only requirement is that these algorithms are consistent. They satisfy what's called the correctness property. So for every message in the message space and every key in the key space, it had better be the case that if I encrypt the message with the key k, and then I decrypt using the same key k, I had better get back the original message that I started with. So this equation here is what's called the consistency equation, and every cipher has to satisfy it in order to be a cipher. Otherwise, it's not possible to decrypt. One thing I wanted to point out is that I put the word efficient here in quotes, and the reason I do that is because efficient means different things to different people. If you're more inclined towards theory, efficient means runs in polynomial time. So algorithms E and D have to run in polynomial time in the size of their inputs. If you're more practically inclined, efficient means runs within a certain time period. So for example, algorithm E might be required to take under a minute to encrypt a gigabyte of data. Either way, the word efficient kind of captures both notions, and you can interpret it in your head whichever way you like. I'm just going to keep referring to it as efficient and put quotes in it. As I said, if you're theory inclined, think of it as polynomial time, and otherwise think of it as concrete time constraints. Another comment I want to make is that in fact, algorithm E is often a randomized algorithm. What that means is that as you're encrypting messages, algorithm E is going to generate random bits for itself, and it's going to use those random bits to actually encrypt the messages that are given to it. On the other hand, the decryption algorithm is always deterministic. In other words, given the key and the ciphertext, output is always the same. Doesn't depend on any randomness that's used by the algorithm. Okay, so now that we understand what a cipher is better, I want to kind of show you the first example of a secure cipher. It's called the one-time pad. It was designed by Vernam back at the beginning of the 20th century. Before I actually explain what the cipher is, let's just state it in the terminology that we've just seen. So the message space for the Vernam cipher for the one-time pad is the same as the ciphertext space, which is just the set of all n-bit binary strings. So this just means all sequences of bits of 0, 1 characters. The key space is basically the same as the message space, which is again simply the set of all n-bit binary strings. So a key in the one-time pad is simply a random bit string. So it's a random sequence of bits that's as long as the message to be encrypted, as long as the message. Okay, now that we specified kind of what the cipher is defined over, we can actually specify how the cipher works, and it's actually really simple. So essentially, the ciphertext, which is the result of encrypting a message with a particular key, is simply the XOR of the two, simply K XOR M. So see a quick example of this. Remember that XOR, this plus with a circle, XOR means addition modulo 2. So if I take a particular message, say 0, 1, 1, 0, 1, 1, 1, and I take a particular key, say 1, 0, 1, 1, 0, 0, 1, when I compute the encryption of the message using this key, all I do is I compute the XOR of these two strings. In other words, I do addition modulo 2 bit by bit. So I get 1, 1, 0, 1, 1, 1, 0. That's the ciphertext. And then how do I decrypt? I basically kind of do the same thing. So to decrypt a ciphertext using a particular key, what I do is I XOR the key and the ciphertext again. And so all we have to verify is that it satisfies the consistency requirements. And I'm going to do this slowly once, and then from now on I'm going to assume this is all simple to you. So we're going to have to make sure that if I decrypt a ciphertext that was encrypted using a particular key, I had better get back the message M. So what happens here? Well, let's see. So if I look at the encryption of K and M, this is just K XOR M by definition. What's the decryption of K XOR M using K? That's just K XOR M. And so since I said that XOR is addition modulo 2, addition is associative, so this is the same as K XOR K XOR M, which is simply, as you know, K XOR K is just 0, and 0 XOR anything is simply M. Okay, so this actually shows that the one-time pad is in fact a cipher, but it doesn't say anything about the security of the cipher. And we'll talk about security of the cipher in just a minute. First of all, let me quickly ask you a question just to make sure we're all in sync. Suppose you're given a message M and the encryption of that message using the one-time pad. So all you're given is the message and the ciphertext. My question to you is, given this pair, M and C, can you actually figure out the one-time pad key that was used in the creation of C from M? So I hope all of you realize that, in fact, given the message and the ciphertext, it's very easy to recover what the key is. In particular, the key is simply M XOR C. And we'll see that if it's not immediately obvious to you, we'll see why that's the case a little later in the lecture. Okay. All right. So the one-time pad is really cool from a performance point of view. All you're doing is you're XORing the key and the message. So it's a super, super fast cipher for encrypting and decrypting very long messages. Unfortunately, it's very difficult to use in practice. The reason it's difficult to use is the keys are essentially as long as the message. So if Alice and Bob want to communicate securely, so Alice wants to send a message M to Bob, before she begins even sending the first bit of the message, she has to transmit a key to Bob that's as long as that message. Well, if she has a way to transmit a secure key to Bob that's as long as the message, she might as well use that same mechanism to also transmit the message itself. So the fact that the key is as long as the message is quite problematic and makes the one-time pad very difficult to use in practice. Although we'll see that the idea behind the one-time pad is actually quite useful. And we'll see that a little bit later. But for now, I want to focus a little bit on security. So the obvious questions are, why is the one-time pad secure? Why is it a good cipher? Then to answer that question, the first thing we have to answer is, what is a secure cipher to begin with? What is it? What makes a cipher secure? Okay, so to study security of ciphers, we have to talk a little bit about information theory. And in fact, the first person to study security of ciphers rigorously is a very famous, the father of information theory, Claude Shannon, and he published a famous paper back in 1949 where he analyzes the security of the one-time pad. So the idea behind Shannon's definition of security is the following. Basically, if all you get to see is the ciphertext, then you should learn absolutely nothing about the plaintext. In other words, the ciphertext should reveal no information about the plaintext. And you see why it took someone who invented information theory to come up with this notion, because he had to formally explain what does information about the plaintext actually mean. Okay? So that's what Shannon did. And so let me show you Shannon's definition. I'll write it out slowly first. So what Shannon said is, suppose we have a cipher ED that's defined over a triple KM and C, just as before. So KM and C define the key space, the message space, and the ciphertext space. And we say that the cipher has perfect secrecy if the following condition holds. It so happens that for every two messages, M0 and M1 in the message space, for every two messages, the only requirement I'm going to put on these messages is they have the same length. So we'll see why this requirement is necessary in just a minute. And for every ciphertext in the ciphertext space, okay, so for every pair of messages and for every ciphertext, it had better be the case that if I ask, what is the probability that encrypting M0 with K, encrypting M0 with K gives C, okay, so how likely is it, if we pick a random key, how likely is it that when we encrypt M0 we get C? That probability should be the same as when we encrypt M1. Okay, so the probability of encrypting M1 and getting C is exactly the same as the probability of encrypting M0 and getting C. And this is, as I said, where the key, the distribution, is over the distribution on the key. So the key is uniform in the key space. So k is uniform in k. And I'm often going to write k arrow with a little r above it to denote the fact that k is a random variable that's uniformly sampled in the key space k. Okay, this is the main part of Shannon's definition. And let's think a little bit about what this definition actually says. So what does it mean that these two probabilities are the same? Well, what it says is that if I'm an attacker and I intercept a particular ciphertext C, then in reality, the ciphertext, the probability that the ciphertext is the encryption of M0 is exactly the same as the probability that it's the encryption of M1, because those probabilities are equal. So if all I have is the ciphertext C, that's all I've intercepted, I have no idea whether the ciphertext came from M0 or the ciphertext came from M1, because again, the probability of getting C is equally likely whether M0 is being encrypted or M1 is being encrypted. So here we have the definition stated again, and I would just want to write these properties again more precisely. So let's write this again. So what this definition means is that if I'm given a particular ciphertext, I can't tell where it came from. I can't tell if the message that was encrypted is either M0 or M1. And in fact, this property is true for all messages, for all these M0, for all M0 and M1. So not only can I not tell if C came from M0 or M1, I can't tell if it came from M2 or M3 or M4 or M5, because all of them are equally likely to produce the ciphertext C. So what this means really is that if you're encrypting messages with a one-time pad, then in fact the most powerful adversary, I don't really care how smart you are, the most powerful adversary can learn nothing about the plaintext, learns nothing about the plaintext from the ciphertext. So just to say it in one more way, basically what this proves is that there's no ciphertext only attack on a cipher that has perfect secrecy. Now, ciphertext only attacks actually aren't the only attacks possible, and in fact, other attacks may be possible. But other attacks may be possible. Okay. Now that we understand what perfect secrecy means, the question is, can we build ciphers that actually have perfect secrecy? And it turns out we don't have to look very far. The one-time pad, in fact, has perfect secrecy. So I want to prove to you, this is Shannon's first results, and I want to prove this fact to you. It's a very simple proof, so let's go ahead and look at it and just do it. So we need to kind of interpret, what does it mean? What is this probability that EK of M0 is equal to C? So it's actually not that hard to see that for every message and every ciphertext, the probability that the encryption of M under a key K, the probability that that's equal to C, the probability of a random choice of key, by definition, all that is basically the number of keys, K in script K, such that, well, if I encrypt M with K, I get C. So I literally count the number of such keys, and I divide by the total number of keys. Right? That's what it means that if I choose a random key, that key maps M to C. Right? So it's basically the number of keys that map M to C divided by the total number of keys. This is this probability. So now suppose that we had a cipher such that for all messages and all ciphertext, it so happens that if I look at this number, the number of K in K, such that E, K, M is equal to C. In other words, I'm looking at the number of keys that map M to C. Suppose this number happens to be a constant. So say it happens to be 2, 3, or 10, or 15. It just happens to be an absolute constant. If that's the case, then by definition, for all M0 and M1 and for all C, this probability has to be the same, because the denominator is the same, the numerator is the same, it's just this constant, and therefore this probability is always the same for all M and C. And so if this property is true, then the cipher has perfect secrecy. Okay, so let's see what can we say about this quantity for the one-time pad. So the question to you is, if I have a message in a ciphertext, how many one-time pad keys are there that map this message M to the ciphertext C. In other words, how many keys are there such that M XOR K is equal to C? So I hope you've all answered 1, and let's see why that's the case. For the one-time pad, if we have that the encryption of K of M under K is equal to C, that basically, well, by definition, that implies that K XOR M is equal to C. But that also simply says that K has to be equal to M XOR C. Yes, I just XOR both sides by M, and I get that K must equal to M XOR C. Okay, so what that says is that for the one-time pad, in fact, the number of keys in K such that EKM is equal to C, that simply is 1, and this holds for all messages and ciphertext. And so again, by what we said before, this says that the one-time pad has perfect secrecy. Perfect secrecy, and that completes the proof of this trivial, very simple lemma. Now, the funny thing is that even though this lemma is so simple to prove, in fact, it proves a pretty powerful statement again. This basically says, for the one-time pad, there is no ciphertext-only attack. So unlike the substitution cipher or the Vigenère cipher or the rotor machines, all those could be broken by ciphertext-only attack, we've just proved that for the one-time pad, that's simply impossible. Given the ciphertext, you simply learn nothing about the plaintext. However, as we'll see, this is not the end of the story. I mean, are we done? I mean, basically, we're done with the course now because we have a way to encrypt so that an attacker can't recover anything about our message. So maybe we're done with the course. But in fact, as we'll see, there are other attacks. And in fact, the one-time pad is actually not such a secure cipher. And in fact, there are other attacks that are possible, and we'll see that shortly. Okay? So I emphasize again, the fact that it has perfect secrecy does not mean that the one-time pad is a secure cipher to use. Okay, but as we said, the problem with the one-time pad is that the secret key is really long. So if you had a way of communicating the secret key over to the other side, you might as well use that exact same method to also communicate the message to the other side, in which case you wouldn't need a cipher to begin with. Okay, so the problem again is the one-time pad has really long keys, and so the obvious question is, are there other ciphers that have perfect secrecy and possibly have much shorter keys? Well, so the bad news is that Shannon, after proving that the one-time pad has perfect secrecy, proved another theorem that says that if in fact a cipher has perfect secrecy, the number of keys in a cipher must be at least the number of messages that the cipher can handle. Okay, so in particular what this means is if I have perfect secrecy, then necessarily the number of keys, or rather the length of my key, must be greater than the length of the message. So in fact, since the one-time pad satisfies this with equality, the one-time pad is an optimal cipher that has perfect secrecy. Okay, so basically what this shows is that this is an interesting notion. The one-time pad is an interesting cipher, but in fact, in reality, it's actually quite hard to use. Hard to use in practice, again, because of these long keys. And so this notion of perfect secrecy, even though it's quite interesting, basically says that it doesn't really tell us that practical ciphers are going to be secure. And we're going to see, but as we said, the idea behind the one-time pad is quite good, and we're going to see in the next lecture how to make that into a practical system.